In this video, we're going to talk about the pigeonhole principle. This idea actually might seem obvious, it's very intuitive. However, it is an extremely important idea that is used to prove many different statements in mathematics. So let's take a look at what the pigeonhole principle says. Well, imagine that I have 9 pigeonholes and I have 10 pigeons. And I know that every pigeon needs to go into a pigeonhole. Imagine that it's raining and all the pigeons want to stay dry, so each pigeon will want to be inside a pigeonhole. Okay, the first 9 pigeons go and each one takes up a different pigeonhole. Then the 10th pigeon realizes that, oh, well, all the pigeons are all taken, but I definitely want to be inside one because I don't want to get wet. Well, what is the solution? Well, this 10th pigeon will tell one of the other pigeons, hey, we'll need to share, I need to go inside. And that is what happens here. Now we have 10 pigeons inside 9 pigeonholes. Well, but this forces us to have 2 pigeons in the same hole. And actually we just need to have, we're forced to have at least 2 pigeons in the same hole. Maybe 3 pigeons are very good friends and they decide to go all together. But what we know it's impossible is to have each hole with exactly 1 pigeon. We have 10 pigeons that need to go into 9 holes. At least 1 hole needs to have at least 2 pigeons. And that is the idea behind the pigeonhole principle. So you can see it is extremely simple, very intuitive. Formally, the pigeonhole principle is telling us the following. If we have 2 sets, A and B, that are finite, if the cardinality of A is greater than the cardinality of B, then function f from A to B cannot be an injection. It is impossible to define an injective function from a set A that has larger cardinality than the set B, our target set. So in this case, set A is set of pigeons and the set B is the set of pigeonholes, right? We wanted to take each pigeon into a pigeonhole, so we go back. This is what happened, right? We put the first 9 elements in our set of pigeons, we map it to a pigeonhole, and then we were left with a pigeon that had to go to the same pigeonhole as another pigeon. I will leave for you as an exercise to prove this statement by induction. So you can prove this by induction in the number of pigeons, and well, the base case would be n equals to 2, and try to run down an induction proof of the pigeonhole principle. How can we use the pigeonhole principle in applications? Well, I'm going to give you 2 relatively simple examples using playing cards, but actually it can be used to prove many different statements. Here we have a set of 5 cards that, well, we draw from a deck of 52 cards, and we draw 5 cards. Well, if we do that, we have that at least 2 cards have to have the same suit. So imagine that I first draw 4 cards, and this is what happens. Well, now the cards are marked pigeons and the suits are pigeonholes, because, well, each card is going to be mapped to their suit. So here we have, well, clubs goes to clubs, diamonds go to diamonds, spades to spades, and hearts to hearts. So far I have 1 pigeon or 1 card in each pigeonhole, 1 card of each suit. Now if I draw another card, well, we only have 4 suits. So that other card, no matter what the card is, will have to be of one of the 4 suits that I already have. In this case, it turned out to be hearts. So now I have 2 cards that are hearts. So we have 2 cards with the same suit. But it doesn't matter. If that card was clubs, then we would have 2 cards with clubs. If it was diamonds, we would have 2 cards with diamonds. So this is an application of the pigeonhole principle. It's telling me that if I draw randomly 5 cards from a standard deck of 52 cards, I must have at least 2 cards with the same suit. Now let's take a look at this other example. Well, we want to find what's the smallest number of cards that we need to pick from, again, a deck of 52 cards to make sure that you get at least 3 cards of the same suit. Maybe you're playing a game and you want to know how many cards you need to draw to make sure you win, and winning means getting 3 cards of the same suit. Well, again, our pigeonholes are going to be the suits. Imagine that you have boxes with the suits. Now, what we're saying is that we want to make sure that we have 3 cards with the same suit that would correspond to having 3 pigeons in the same pigeonhole. Okay, I draw my first 4 cards and it turned out that all of them had different suits. Okay, sure, that's the worst case scenario. Then I draw another 4 cards and let's see what happens. Well, I draw 1 is hearts, so I have 2 hearts so far. Get another 1 is diamonds, so I have 2 diamonds. Get another 1 is spades, so I have 2 spades. Get another 1 and it turns out to be clubs. So at the moment I have 2 cards of each suit. Well, what happens now when I draw an extra card? Well, that card would have to go into one of these 4 categories that I have, because there are only 4 suits. It has to go to one of those. Well, if I pick clubs, I have 3 clubs. But if, let's say I get something else, maybe it was hearts, then I would have 3 hearts. So this shows that now I have 3 cards of the same suit. So the worst case scenario, after drawing 8 cards, well, I could end up with 2 cards of each suit after 8 cards. But then when I get the 9th card, that will have to go into one of those 4 categories, bringing up the number of cards with the same suit to 3 for one of these 4 slots. So we need 9 cards. So imagine that you're playing a game and you win if you get 3 cards of the same suit, and you have to blindly draw cards, cannot take a look at them, and you want to be 100% sure that you're going to win. But maybe you have to pay some money for each card you draw. Well, you want to minimize the amount of money that you spend getting your cards, so you want to get as few cards as possible. You want to get the minimum number of cards that will guarantee that you're going to win. In this case, you need exactly 9 cards to be 100% sure that you're going to have at least 3 cards with the same suit.